Hello guys, today I'm going to cover Torsion Springs. So we're going to continue, and this is going to be the last lecture on springs. And I'm pretty sure most of you are familiar with the torsion spring. The torsion spring is basically you bring on a wire, right, and you sort of like wrap it around multiple times, right? And then this guy is gonna go below this, and then you wrap it up, and then ultimately it's gonna come from below, right? And what you are going to have is you are going to have you basically apply forces on it, and what will happen is these forces are going to develop stresses on it, right? And I'm going to call this guy F, and let's say that distance over here is going to be L1. And let's say this guy is F1 and you have another force over here, and that distance here is actually L2. Okay. So this guy is essentially going to behave as a cantilever beam, and this guy as well is a cantilever beam. And the cantilever beam, if you have this force applied, it means that over here you are going to be under what? Compression, right? And on this, so this guy and this guy, right, both of these points are going to be, like, say, under compression. And anywhere, as a matter of fact, on the inner of this guy is going to be compression, and on the outside it's going to be tension, right? So this guy is tension, and then on the outside is going to be tension. So obviously this guy is going to be in equilibrium, meaning that the moment, right, is going to be equal to F1 times L1, which is going to be equal to F2 times L2. If L2 is shorter, then F2 would have to be greater. But what really happens is that once you get into the coil, you have no more forces, essentially you have that moment. So anywhere along this wire right here, once you cross that point, you are going to have a bending moment applied on that wire. And again, inside the wire, you are going to have here compression, and then on the outside of the wire, you are going to have tension. And what we are going to do is you are going to have here axial stresses, and then here axial compression stresses, right? So here axial tension stresses, and at the bottom or on the inside, you're going to have axial compression stresses. So this is really the equation of this. And we know in the case of when you have a bending moment and then you have a circular cross section, your stresses is going to be equal to the stresses are going to be equal to KIO MC over I. So I know the stress is going to be equal to MC over I, and I is on the inner fiber and then O on the outer fiber. So the stress anywhere on the inner side of the wire, you're going to use KI, and on the outside, you're going to use KO. MC over I, M is the moment inside the wire, which is either F2 times L2 or it's going to be F1 times L1. We know C is going to be the distance from the neutral axis to the surface, right? How about Ki and Ko? Ki is going to be given to you, and then this is from the notes, 4C squared minus C minus 1. Divide that by 4C C minus 1, and Ko is going to be 4C squared plus C minus 1. Divide that by 4C times C plus 1. And it turned out that Ki is actually greater than Ko because you have C minus 1 here, and then on here you have C plus 1. So if your Ki is greater, it means that you're going to have more stresses on the inside than the outside. All right, so your sigma, your maximum stress on a torsion spring is going to be equal to the stress that occurred on the inner fiber, and you're going to use Ki multiplied by MC over I. Okay, and that would be, if that distance is here F times L, if the two if that moment is F times L, right, then it would be equal to Ki 32 FR over pi d cubed, because we know it is going to be a the moment of or the moment area moment basically of a circle is going to be equal to pi d4 over 32, right? So, all right, guys. So this is the maximum stress on a torsion spring, and now I would like to go over. So as a result of this force, right, you are going to develop some rotation, all right, and that rotation is going to be. So I'm going to redraw this one more time. So this is your torsion spring, and then simply like I'm going to try to simplify it. This is, you know, at the level of the wire, right? So let's say you have here, this is your F, and then that is your L, and then on this end you're going to have F, and then that distance is going to be L. So the moment anywhere here is going to be equal to F times L. Now let's look at the actual rotation that occurs. So it turned out that there are two ways for getting the rotation. Obviously, you can, like, you know, integrate the rotation in all the elements, and you know, you would do this in graduate courses. So the analytical solution for the deflection of this wire is going to be given by theta is going to be equal to 64, and all you have to do is just, like, you know, memorize this, or, you know that it exists for our exam in case this came up or in your project. L1 plus L2 divided by 3 pi d. Okay, what that is the deflection that occurs. So this is theta is a deflection of one of the lines, right? So if that line here is fixed, then here we are looking at the deflection of this line. And we know the angle theta is going to be an absolute angle between this current position and where this line is going to be. Let's say you tension this guy, and now this line is over here right now as a result of this force. Then this is going to be your angle theta. All right, and theta is measured in turns. M is the moment, D is the mean coil diameter, D and then E, you all know what it is. NB is the number of body coils, right? And L1 plus L2 divided by 3 pi D. So this is needed to take into account the fact that this lens actually will deflect, and this lens will actually deflect. When you apply a force, basically this line alone, like let's say this guy was fixed, then this guy itself is going to do like something like that, right? The leg itself is going to deflect. So by incorporating those two, L1 plus L2, we mean that this leg is deflecting and this leg is deflecting, right? That is why I have L1 plus L2, and then I'm adding this to the deflection of the body core, right? So L1 plus L2 divided by 3 pi d, essentially I'm mapping the lengths of these two, and then I'm adding those up to the number of body cores. So just be careful later on, like, you know, I might give you, this is like, you know, greater lengths, etc. So you have to still have to basically incorporate that inside your equations. So this is the analytical solution, and it turned out that the analytical solution is not very accurate because, you know, this is a spiral, right? So it, you know, revolves and it goes up. So it turned out that there is actual an empirical equation that was done with testing, and this is a more accurate result. So again, here theta is in turns, right? So if this was a quarter of a turn, then this guy has related by, it's here, right? So this is a quarter turn. So here theta is going to be equal to 0.25 turn. Okay, so theta is going to be measured in turns, okay, not radian, only in this particular situation. So it turned out that so you're not going to use this. This is not a very accurate solution. You're going to use the empirical solution, and the empirical solution is going to be, instead of 64, you're going to replace it by 10.8. So not 64, it is going to be almost, you know, 6 times less. MD D4E, and then MB plus L1 plus L2 over 3 pi D. And by, again, you know, L1 and L2 are counting into effect the deflection of the legs. And I can actually call this whole thing an A, which is number of active coils. This is what we have been doing in the case of compression springs. So 10.8 MD and A. So an A is going to be equal to this value divided by 3 pi D. Okay, so it's really basic. If I have a moment, right, I have a mean coil diameter. This is actually, no, this is D4 over E, right? D4 to the power E. Okay, so theta is going to be equal to 10.8 md NA divided by D4E. And again, theta is measured in turns. Okay, now that I have a relationship between theta and the moment, we know that M is going to be equal to K times theta, right? Where theta is going to be your, where K is going to be your stiffness, right? So torsion spring stiffness. And simply K is going to be equal to M over theta, right? So I can use that relationship and then I can pull K. And if you do this, obviously, you're going to get K is going to be equal to M over theta. And I'm going to use here the empirical solution. That's going to be equal to D4 E divided by 10.8 T times NA. All right, and this is the stiffness of your torsion spring. Okay, so there is one thing that is very important that we should take into consideration in the case of torsion springs. In the case of the torsion spring, I know this guy is going to have an inner diameter, right? And let me continue this guy. And then this is, let's say, my torsion spring. And as a result of, applying these forces, F1 and F2, I'm going to essentially shrink the inner diameter of the torsion spring. All right, usually every torsion spring will basically have a pin on the inside. And this pin is used to basically to be able to utilize that torsion spring effectively. You have to have like a pin, right? And then the pin will prevent this guy from going up or down, right? So usually there's a clearance between the pin. This is, let's say fixed to, some structure that you have developed. So this is, plate, and then this pin is actually inside the plate, and this is your torsion spring. So that pin basically could have some diameter, right? And I'm gonna call this guy, let's say this is diameter of the pin. This is fixed diameter. So as a result of applying a moment, this diameter will actually shrink, and we're gonna call this guy d prime. So d prime is gonna be equal to NB divided by N prime multiplied by D. So D is going to be the original, this is the mean coil diameter. So this is original mean coil diameter. And in this case, it's going to be that distance, right? Okay, the mean coil diameter of the torsion spring is always, like I said, it's going to be from the, to the middle of the wire and the middle of the wire. And where N prime itself is going to be equal to NB plus theta C. Okay, so we get, so theta C is going to be the deflection of the coil itself, not including the deflection of these wires, all right, or the legs. So D as a, sorry, D prime is going to be U mean coil diameter. This is original mean coil diameter D. And B, I know the number of body coils, so this has to be given to you. All right. Theta C, you're going to get it from the deflection of what? Deflection of the coil itself. All right. How much this coil has rotated. And theta C, I know we just calculate theta. We calculate the deflection of this whole thing, but let's say you want to calculate the deflection of this point. So essentially, you're going to see by how much this point is going to move. And that angle right there is theta C, like how many turns a point here will move as a result of the deflection of here. And theta C, it's going to be equal to, using the empirical result, MD times NB over D4E. Here, before I used NA, right? So when I was looking to get the deflection of the actual wire, theta, I'm using number of active coils where it is equal to MB plus L1 plus L2 divided by 3 pi D. In the case where you are looking for the deflection of just the coil itself, you don't need to include L1 plus L2 over 3 pi D, right? So you just need to look into NB. And this will give you how much a point here is going to travel as a result of this moment, right? So, and this is going to be again in turns, right? So in this case, that would be like 1/16 of a turn. Okay, so this is your theta c. So we take this guy, and now this guy is going to be here. And as you can see, if theta c is 0, then d prime is going to be equal to d. So if the coil had no deflection, then your new mean coil diameter is equal to the original mean coil diameter, right? But if theta c is larger than 0 as a result of some bending moment, then obviously d prime is going to be smaller than d. Now, if I were to look at the clearance, the inner diameter will actually be equal to, so the final inner diameter is going to be equal to d prime, right? Minus, so I have a half a diameter, half wire diameter on this end, and then half wire diameter on this end, so it's going to be minus d, right? So this is your diameter, right, of the inner coil of your wire, right? So by that, what I mean here is that this is your coil, right? This is your coil, and let's say obviously this guy is wrapping up around it, and then ultimately you have this. So here, this is your di, right? Di is going to be this, okay? This guy is going to be di, and obviously if you have some sort of a pin, right, and pin is fixed to the wall, I can always get the clearance between them, right? The diametral clearance, it's going to be a di minus the pin, right? So clearance is going to be equal to how much? Di minus d of the pin, diameter of the pin. And that clearance always has to be positive, right? If this guy is negative, it means that you are developing some, you're essentially, you're trying to develop some plastic strain on the legs, for example, right? Because you can no longer compress the coil of the body. Okay, so that is regarding the equations that govern this type of torsion springs. What I would like to also include is, so right now we have the bending moment, right? Like I said, the bending moment, the maximum bending moment on a torsion spring is going to be equal, is going to occur on the inner fiber, and that is going to be equal to 32 FR divided by pi d cube, which is essentially 32 times the bending moment, right, which is happening on the wire. Okay, if you want to look at the limitation, so what could be the maximum force or diameter of the wire, etc., for a given stress to yield? So this is going to be limited by your maximum stress, and the maximum stress, and this will fail in yielding, is going to be equal to Sy. And Sy is going to be equal to a bunch of values depending on which wire you are using. It would be equal to 0.78 SUT for a music wire. And we said the majority of springs utilize music wires. And if it was hardened and tempered carbon steel, it's going to be equal to 0.78 SUT for a hardened and tempered carbon and low alloy. So that is a table for these low alloy steel. In our case, mainly we're going to be dealing with this guy, and you guys know how to solve this, right? You guys know how to get SUT. SUT for a music wire is going to be equal A d to the power m, right? And that is a lookup table for this. All right, I'm going to do a quick example, which is in our notes. And in the example, we have a stock torsion spring that is made of, so this is an example. So we have a stock torsion spring made of a diameter, so small d is equal to 0.0782 inch, and the music wire, and it has number of body coils is going to be 4.5 turns. Inside the coil is a pin having diameter of 0.4. So diameter of the pin is going to be equal to 0.4 inches. The coil outer diameter, so DO is going to be equal to 19 over 32, which is 0.593 inches. We need to find the maximum allowable torque and angular deflection. So find Tmax, right, and theta. Theta, like I said, is going to be in terms. Okay, how are we going to do this? So let us actually draw this to get an idea how this would look like. So we have a pin, right, and the pin diameter here is 0.4 inches, right, and then we have the wire is going to be around that pin. This is your spring. Okay, and obviously here, and they gave us your outer diameter for this, as given to us as how much? 0.593 inches. We would like to find the maximum torque applied. So here we're looking simply at the torque inside this. Okay. And they actually, if you look at the drawing that we have in this example on lecture 21.5, they gave us that you have, like force applied over here, right? And the force is actually applied at 1 inch. 1 inch. So by the way, this leg could be longer, right? But we don't really care about this portion because this portion is not going to be loaded. So the deflection of the coil is not going to account inside theta or theta C. Okay, so we don't actually include that. We just look at the lengths where the force is applied. So I have 1 inch on this end, and on the figure that, in a problem, basically, this guy is at a 90 degree. It doesn't really matter. When you're looking at theta C, you're looking at the relative deflection between where this line is and where this line is going to be. And then you can always get the angle between where the line was and now the new orientation of the angle. Okay, so we need to find the maximum torque. So what we are going to use is we know the maximum is going to occur on the inside. We're going to set up our equation and then we're going to solve for the torque. So we know that sigma max is going to be equal to sigma max is going to be equal to Ki 32 torque divided by pi d cube. And I know, so from here, basically, I know this guy has to be equal to my yield, right? So we can find the torque is going to be equal to sigma y pi d cube divided by 32 Ki. All right, so we need to know, we need Sy, okay, which is, sigma y in this case. And we need to also calculate Ki and Ki. So how do I find Sy? We said Sy will be equal to 0.78 SUT, which is going to be equal to, and we know it's a music wire, so it's going to be AD to the power M, and then we know 0.78 A is going to be equal to 201. Wire diameter is 0.072, and then if you look at the exponent here, it's going to be 0.145. This is from table 10.4, right? 10.4 in our notes. And from here, if you solve Sy, you're going to see that Sy is going to be equal to 0.78 multiplied by 294.4, which is equal to 229.6 KSI. Okay, so we got Sy, we still need to find Ki. Ki is going to be equal to how much? Ki is going to be equal to 4c squared minus c minus 1 divided by 4c c minus 1, and we know c is going to be equal to the spring constant d over d, but what d? Here they gave you the outer diameter, guys, so we have to bring it to the mean coil diameter, so we remove half a diameter on either side, so it's going to be one diameter, so 19, so 2 minus 0.072, and that guy is going to be equal to 0.072 inches. Okay, so Ki is going to be equal to, replacing this value over here, you're going to end up with 1.115. So you got your Ki. Now we can solve for the torque based on this equation, and then your Tmax is going to be equal to 229.6 times 10 to the 3, because this value here is in KSI, right? So you want to put that in pounds per square inches, we're dealing with inches here, multiplied by pi times 0.072 to the power 3, diameter cube, wire diameter cube, 32 1.115, and in that case your torque is going to be equal to 7.55 pound times inches. Okay guys, so this is how you calculate the torque. This is drifting for some reason, so there you go. Okay, and next step is we would like to find the spring, we would like to find the maximum deflection, right? So they ask us to find the angular deflection. Well, obviously, angular deflection has to be here at the maximum torque, right? Or I could ask you to find the angular deflection, right, at any given torque. So obviously, I'm going to specify this very precisely for you guys. And what we'll do is we can simply use the equation that we have, or you can choose to find the spring rate. We know T is going to be equal to K times theta, right? So if you have to have the deflection, we know theta is going to be equal to T over K. We need to know what is the value for K. K is going to be equal to D4 E 10.8. So it's not 64 here because we're using the empirical. NA, and again, guys, NA will include the number of body coils, plus we're going to include the fact that the legs could be deflected. All right, so the first step is you have to find NA, which is equal to NB plus L1 plus L2 over 3 pi D, which is equal to 4.25, 1 plus 1 inches on either end, divided by 3 pi multiplied by 0.5218. And this guy is going to be equal to 4.657 turns. And then number of coils is going to be in turns, right? So K, now simply I'm going to replace these, and I'm going to end up with 0.072 to the power 4 multiplied by 28.5 times 10 to the 6. This is the modulus of elasticity of the music wire. And 10.8, 0.5218 multiplied by, this is your mean coil diameter, multiplied by number of active coils. It's going to be equal to, so your stiffness is going to be 29.18 pound-inch over turn. If you want to get the actual rotation, then it's going to be, like I said, T over K, and 7.55 divided by 29.8. And that would be in turns, basically, right? And so if I want to convert a turn to degrees, I can multiply it by 360. If you do that, you're going to get 93.24 degrees. So it's almost quarter of a turn. Okay, so this number 7.55 divided by 30 is almost 0.25, and that is a number. Okay, guys, so this is what you need to know in terms of the static force analysis in the case of the torsion spring. And the last thing that we want to see is we would like to see what happens inside the diameter as a result of this moment. So we said we can always find the new mean coil diameter, and the new mean coil diameter is going to be equal to NB divided by NB plus theta C, where theta C is a number of turns in the coil itself. We need to get theta C, so theta C is going to be equal to 10.8, the maximum torque, right, times D times NB. Here it's NB, not NA, right, because we're only looking at the deflection of the coil itself, right? So here we're trying to use theta C to plug it here and then find the new mean coil diameter and then see if there would be interference between the spring and the pin. So if you do this operation, you are going to calculate D prime, and D prime in this case is going to be equal, or let's at least you can calculate like first theta C. So theta C is going to be equal to 10.8 multiplied by 7.54 multiplied by mean coil diameter 0.5218 multiplied by number of body coils, which was 4.25, right? And then we're going to divide this by D to the power A, so 0.072 to the power 4 multiplied by 28.5 times 10 to the 6. and this value for delta C is going to be in turns, and this guy is going to be 0.236 turns. Okay, we got delta C. Now we can get D prime. D prime is going to be equal to MB, right? Which was equal to 4.25 divided by 4.25 plus 0.236, and this is multiplied by your mean core diameter, and that is going to be equal to 0.422 inches. Okay, now if you want to see if there is interference, how do you do that? So you're gonna get I'm sorry, this is 0.494. This value is going to be 0.494, and then this is in the notes. Okay, 0.494. This is what, this is the new mean core diameter. If you want to get the inner diameter, then di is going to be equal to 0.494 minus your wire diameter, which is 0.72 inches. 0.72 inches, and your dr is going to be equal to 0.42 inches. Now we can compare this number to your pin diameter. D of the pin was equal to how much? 0.4. So clearance, and this is diametric clearance, right? Clearance is going to be equal to 0.422 minus 0.4, which is 0.022 inches. Okay, guys, so that is what you need to know regarding the static failure of, or the yield failure of torsion springs. The last part in this exercise is we're going to look at the fatigue failure of torsion springs. And we know there are a couple ways what we could do. We could either use this equation, SF is equal to SA over sigma A, where we solve for the alternating stress, and we look up SA from a lookup table. And we can obviously use any of the criteria that we had, modified Goodman, Gerber, etc. So in this problem, in this part, if I tell you that the torque on this torsion spring is fluctuating, which is basically F times L in that case. And if that torque is fluctuating between 1 pound per inch to 5 pounds per inch, what is your safety factor based on, in this case, the Gerber criteria? How do you do that? So first of all, we can find the alternating, which is the maximum minus the min divided by 2. 5 minus 1 over 2 is equal to 2, and then we can get the mean torque, T max plus T min divided by 2, and then you are going to end up with this. So now we have the alternating the alternating and then the mean torque. We can then find the alternating bending stress and the mean bending stress inside the wire that makes up the torsion spring. And these equations are already provided to you. We said the maximum stress is going to occur on the inner fiber. So we can get sigma A from this, and then we can get sigma M. Again, here, instead of redoing all these equations, we know sigma M and sigma A are related by the portion of the torque, the mean over the alternating, or you can simply reuse that equation. So you can say sigma M is equal to Ki, so 2Tm divided by pi d cubed, so you're going to get this guy. So we have the alternating and then we have the mean. Let's say I use the safety factor is equal to SA over sigma A. I need to look up SA from based on Gerber criteria. This is going to be my SA. And what you would see is, R is going to be the load ratio, right, which we already described. R is equal to TA over TM, or sigma A over sigma M. So the only missing components in that expression are SE, right? So the only missing thing here is SE, and then we already calculated SUT for the music wire, which is A over D to the power M, and I believe it was 294.4. So to calculate the endurance limit, you actually have to use this equation right there, right? So this is your equation that you need to do here to calculate your SE. And SE here is going to be a function of this guy, which is SR, right? SR is actually the fatigue strength of this. You just need to know this equation, and you need to know how to calculate SR. And you're going to calculate SR based on this table. And based on this table basically relates your, if you read this carefully, right, this is bending stresses, recommended bending stresses. That by that they mean actually SR, for a helical torsion spring as percent of SUT. Okay, so percent of SUT. So these numbers here are the percentage. So if I calculate SR, right, SR is going to be in a case of a unpeened, like regular spring, and we use for 10 to the 6. This is 1 million cycle basically is our endurance limit. So just remember, SR is going to be 0.5 SUT. All right, so SR is going to be equal to 0.5 SUT in this case, and if it was shot peened, it would be 0.6 SUT. All right, so this is what I have here. So SR is going to be equal to 0.5 SUT. So once you calculate this SR, you're going to come back and then you're going to plug it here, and you can find SE. So you already calculated SUT based on equation A over D to the power M. You have SR. You have SUT, and then you calculate SR based on this table, and we always look at 10 to the 6 cycles, whether it is not shot peened or shot peened. And this was for ASTM A228, and this is for these two types of wires. And just calculate SR, you plug it here, you got SE, and then now you can actually get SA. So it is pretty straightforward. So SE is going to be equal to SUT over 2, which was 294.4 divided by 2, which is 147.2. And then replacing that in this equation, you're going to end up SE. Your endurance limit would be 78.5 KSI. Now just replace whatever that we had for SA, and then you got it here, and then your safety factor is going to be equal to SA of sigma. Okay, so the key here is to realize that how you get your endurance limit in order to use it in that equation. And the key to get the endurance limit of a torsion spring is to use this equation. And this equation has inside it SR. How do you get SR? You get SR based on this table. And these numbers here are not 50 KSI. This number is percent, right? So 0.5 or 0.6 if it was shot peen made of this. Pretty straightforward. If I were to ask you, find the maximum reciprocating torque for infinity life, you can use this equation, and this is again the Gerber, and then in this case you simply set the safety factor to be equal to 1, and we know how to relate the alternating and the mean in the case of a torsion wire, and then obviously we know in this case the smallest torque here, maximum fluctuating torque from 0, obviously here in this case. So 0 is going up to T, and then 0 to T. So we can relate the alternating to our torque, right? It's going to be half the torque in that case, and the mean again. So if this is your torque, your alternating torque is going to be T over 2, and your mean torque will always be T over 2. So that is why we have T times 0.5 and then T over 2. So this will depending how I tell you how the torque is fluctuating. If I tell you the torque is fluctuating, positive T and then minus T, in that case your mean would be 0, right? And then your alternating would be T, right? So depending on this diagram, you can get sigma and then sigma m. Pretty straightforward over here. And then once you have sigma and then sigma m as a function of T, you can either write the safety factor is equal to SA over sigma A, and then you can get this T, or you can simply use that equation, which is basically the same result. So once you have safety factor is equal to 1, you have T here, and then T here is the power square. You have this equation, the quadratic equation, and then you solve for it. When you have this equation, basically you'll have one torque to be positive, and then the other one could be negative or complex. It won't be complex, by the way. This will always be one of the roots will be negative, and then this is going to be your torque. So this, you need to apply a torque below this guy, so you have a safety factor of 1. So that way your spring will just last about infinity. Okay, guys, so if you have any questions regarding any of the items that I discussed on springs, please do feel free to reach out to me, and I'll be able to explain all that to you. Overall, the material is, reading the material and then doing the lectures should help you very well. If not, then you can see me during my live office hours. Okay, or just reach out to me, and I'll be happy to explain it to you.